Okay, guys, are you able to hear? Hello?
Hello, sir.
Okay, so I hope you're able to hear. Good. So let me share my screen. I can start right away. Okay, hope you're able to see my screen. You're not able to hear me. 1 second. Guys, I think now we are able to hear.
Yes, sir.
Yes, now you're able to hear.
Yes, sir.
Hello?
Yes, sir.
Hello?
Yes, sir.
God. Okay, you're able to hear. But can you speak something?
Sir, can you hear us?
Is anyone
Hello?
not able to hear? We spoke right now. Oh God. We can hear you, sir, but I'm not able to hear you. That's a bad thing. I don't want it to be like this. Wait, I'll connect it to my normal audio itself. I'll just switch it off. Okay, guys, speak something now.
Can you hear us, sir?
Okay, fine. This is fine. Fine. How about my voice? My voice is okay?
Yes, sir.
Okay, cool. Right. Let's start it right away. Sorry, guys, it became a little late. My laptop was updating some firmware or something and it became late. Okay, cool. So, yeah. So, if you can remember, right? So, we were speaking about something, a new thing called as,
Entropy.
sorry, what is it?
Entropy, sir.
Yeah. So, we're talking about entropy, right? So, what did I tell you? What is entropy?
You told us a measure of disorderliness, sir.
Correct. Right. So when I say entropy, the first thing which should come to your mind is chaos, disorderliness, randomness. Right. All these are the words which should come to your mind. Right. How randomly oriented the molecule is, or say how random the process is. Right. So all these that's what will come to your mind. So basically, how much is this how much is this chaos? How much is this randomness? That measure is what is called as your entropy. Right. We gave a mathematical definition also for that, and I told you that we will not be able to measure the absolute entropy. We'll be able to measure only the change in entropy, right? So the absolute entropy is denoted by the letter S, right? And we are not going to, I said we'll not be able to directly measure it. What we'll be able to measure is this delta S, and I told you that it's going to be equal to Q reversible divided by temperature. That Q is the heat and T is the temperature. Right? And I also told you why is it that the Q is in the numerator and T, that is the temperature in Kelvin, is in the denominator, right? So because when I already have higher temperature, right, the increase in entropy will be very small. But when I have initially low temperature, the increase in entropy, or say the change in entropy, will be very, very high, right? And obviously, the more and more heat you supply, more and more will be the change in entropy. So that this particular formula is logically understood, right? Okay. Now the next question is, why is this reversible? Is the next question. Like even in your book, even in your NCERT textbooks, they would have given Q reversible by T, right? And I mean, obviously, not only in NCERT, wherever they have given some good chemistry, right? So definitely they mentioned this Q as Q reversible and not just Q, right? Now the reason is people. So what I want, please understand this entropy change in entropy is actually I want it to be a path function, right? I want my delta S to be a path function. Sorry, state function. I'm really sorry. I want it to be a state function, right? Now we know what is the difference between state function and path function. I think, let me ask someone. Okay, maybe Rahul, are you there? I think if you're not there, just please tell me in the chat. Yes, Rahul. Can you tell me what is the difference between a path function and a state function, or a path variable and a state variable? Hope you're typing. State function is described as a particular state. Okay, fine. So in simplest words, how can I put it? In simplest words, I can say that your state functions are just going to depend upon what is the initial state and what is the final state, right? So when I say state, I'm talking about the conditions. Basically, what is the initial temperature, volume, and pressure, and what is the final volume, PVT, initial PVT, final PVT. PVT is pressure, volume, and temperature. So when we already discussed this, right? When I say state of a system, when I say state of a system, that means I'm talking about what is the conditions in which the system is present. What is the pressure? What is the volume? What is the temperature? Right? So state functions doesn't depend on anything else but just the initial state and the final state. But when I'm going for path function, right? And I'm going for path function, yes, these two are also important. Yes, it depends on that too. But other than that, they also depend on the path taken from the initial state to the final state, what path you take, right? So I told you the graph will be different, right? So I mean, it depends on the graph. Basically, all the path function will depend. Basically, the path taken, the work is actually a what is that path function? Q is the path function, right? Okay, so what we're telling is we are talking about the reason for why am I having this Q reversible here. And I told you the reason is that I want delta S to be a state function, right? Now, how is it that if I put reversible there, it becomes a state function, right? So please understand my Q, as I told you, is a path function. It depends on the path, right? And temperature is nothing. Temperature is just a variable. We cannot say whether it's a path variable or I would say it's a state function. But anyways, you don't have to worry about it. Temperature, we cannot speak like that, right? Fine. So if already Q is a path function, right? How is it that then delta S will be a state function, right? So for that only we say we are going to make the path constant, in the sense we are going to take only the reversible path. As simple as that. So we're making the path constant, right? This path here is a constant path. When I say reversible, there is only one way by which there is only one path the particle or the system can go, right? So when but if it's reversible, yes, I have so many different paths, right? But when I say reversible, there is just one path possible, and that is a reversible pathway that is very, very slow. We know all those things about reversible processes, right? So we are making delta S a state function by making sure that you put the reversible. When I put reversible, what is happening? I'm making the path constant. There is there is no other path. Only the reversible pathway is allowed. That's what we say. That is the importance of this Q reversible. Is that cool? Right? But how to put it? In all your problems, right? So whatever the Q they give you, I don't think the problems will come for delta S. I have, like, at least not for your NCRT. Anyways, even if it comes, right? You don't have to worry about this Q reversible. So whatever the Q value they give you, right? So you directly substitute it and get the answer. But the actual definition is actually going to be Q reversible by T, right? Okay, fine. So now we understood what do you mean by entropy? What do you mean by change in entropy? Right. Now let me ask you a question. So if I write this reaction, I have N2 plus 3H2 gives 2 ammonia. Now tell me, delta S for this reaction is positive or negative? Just think about it. I have N2 plus 3H2 giving 2 ammonia. Delta S is positive or negative? Okay, let me take a vote. I think that will be fun, right? So how many of you say it's positive? We can put it in the chat. I think it's better to put it in the chat. Just type positive or negative. How many of you say it's positive? I guess 0. Okay, so I'll take that also as an answer. Fine. So I have 3 choices then, right? So I have 0, positive, negative. What about others? How many of you say it's positive?
Sir,
Yeah.
could you explain how to do this, sir? I didn't
Yeah, I will
understand.
definitely tell you how is it. But just I'm asking you, what do you think? I'm definitely gonna give the answer. I'm gonna explain you.
Don't
But I'm
know,
just taking a
sir.
vote. And just vote for it, either positive or negative. Everybody, just put it in the chat. Positive or negative. What do you think? Just a guess. Quick. Okay, positive. Rohan says positive. Then we don't have much time, people. Okay. Shruti says positive. Venisha says negative. Okay, then Bhavadarni says positive. Okay, so more votes for positive. And there is one answer for 0, and Venisha says negative. I have one, two. Yeah, Pranav says positive. Okay. Others, quick. Mithun, Surya, if he's there. Okay, fine. I think they're not answering. Cool. So how do we go about this? If you remember last class, I gave you a reaction. So if in the reaction, what I did, I had CaCO3 on heating gives CaO plus CO2, right? So I told you these are solids and this is a gas here, right? So and we discussed, when I have solids, liquids, and gases have the maximum entropy, isn't it? Right? Gases have maximum entropy because they are the one which is who are more like, say, most disoriented, like most random, isn't it? Right? So for this reaction, if I ask you, right, what will be the delta S value, whether it's going to be positive or negative, now you can easily see that there are solid in the reactant side. Obviously there is one solid in the product side also, but in the product side I have one gas, right? So obviously solids are getting converted to gas. So what happens? Entropy is increasing, isn't it? So whenever you see entropy is increasing, so definitely for this reaction the delta S is positive, right? Okay, but if it's a reverse reaction, CaO plus CO2 giving CaCO3, for that reaction it will be negative because gas is becoming a solid, right? Okay, now in this case, right, for ammonia case, right? Now you can see all our gases, right? All our ammonia is a gas, N2 is a gas, H2 is a gas, everything is a gas, right? But what you can understand is in the reactant side, I have 4 molecules of gases, one N2 and 3 H2s, right? And on the product side, I just have 2 molecules of gases, that is 2 moles of ammonia or 2 molecules of ammonia, right? So what is happening to the gas content? The gas content is actually decreasing from 4 moles, it's becoming 2 moles, right? So obviously the amount of gas content in the reactant side, I have more gases, and the product side I have less gases. So obviously more gas will have more entropy, less gas will have less entropy. So in this case, the delta S is negative, right? So hope everybody understood. Rohan, is it okay?
Yes, sir, understood.
Right? So you just have to look for gaseous species. Obviously, you just have to remember that solids have the least entropy than liquids, and gases have the maximum entropy. Like this, if you can understand, right? Yes, you will be able to answer these kind of questions, right? For this, whether it's positive or negative, you'll be able to easily answer. Is that cool? Right? Okay. So yeah, let us continue. Right? Okay. Now, as I told you, we are going to see second law of thermodynamics, right? So actually the second law, and yeah, one more thing before we move on, I'll tell you what is this, right? So how do we have this system and surroundings, right? So obviously, right? So when I say universe, right? So universe is actually comprises both of your system. When I say S bar M, it's system, people. It's just a short form of writing it. System plus surroundings. Is it not? Right? So same way, like for any of the thermodynamic properties, say delta H, delta U, or what, like say Q, or whatever the thing is, if you want to calculate the universe's value, say if you want to find the delta H of the universe, so what you have to do, basically you have to sum up the delta H for the system, right? And you have to add that with the delta H of the surrounding. So you'll be getting the entire universe's delta H, right? In same way it works good for, and actually this particular thing works best for your entropy. Okay, so now how will I be able to write it is delta S universe will be equal to delta S system plus delta S surroundings, right? So this you have to remember. Not remember, it's purely logical, you don't have to remember anything, right? So the universe's value, right, the entire universe's value of entropy, change in entropy, is a sum of delta S system and delta S surroundings, as simple as that. Okay, right, fine. So basically why am I telling you this now is because the second law is going to be based on this. Okay, fine. Now we are going to see the most, I would say, when this statement came, right, when the second law of thermodynamics came, it is one of the most powerful statements of that particular century. Okay, and one more thing about second law is there are various ways by which you'll be able to interpret the second law. There are basically different scientists gave different statements for second law. Say one of the statements is talking about this delta S universe, right? And the other one will talk about engines, right? But essentially everything leads to the same thing. Like that's what you need to know, right? Okay, so we'll see all the statements possible, right? Fine. So we are going to see second law of thermodynamics. Right now I would say there are two important statements. Only those two statements we'll see, right? Other statements are not important to us, at least not for your level. Okay, fine. So first one, the first statement of second law of thermodynamics, please take down, people. Right, for a spontaneous change, the direction of the process for a spontaneous change, comma, the direction of the process should be in such a way, should be in such a way should be in such a way that the entropy of the universe, such that the entropy of the universe is increasing, is increasing. Okay, I'll repeat the statement. What I told is, for a spontaneous change, comma, the direction of the process should be in such a way that the entropy of the universe is increasing. Okay, so we'll analyze the statement for a while, right? So the first thing you need to understand is, what is this spontaneous process, right? What is this spontaneous process, right? So as simple as that, I can tell you that for a spontaneous process, you don't have to do anything. It happens on its own. Very, very simple. Say what can be spontaneous processes? Say water, when you see a waterfall, right? Say the waterfall will come down from a higher level to the lower level. That's a spontaneous. You're not doing anything. It happens on its own, right? Say for example, if I have ice cubes, if you take it out of the fridge and if you keep it at room temperature, you are not doing anything. It automatically melts, right? Say for example, you put sodium and chlorine together, right, in a bathtub, in a reaction bath, right? You are not doing anything. You are just you're just keeping them in contact and nothing else, and the reaction happens on its own, right? So wherever you see, sorry, excuse me, right? So wherever you see things happening on their own, right, are what are called as spontaneous processes. Okay, but say what can be a non-spontaneous process? A non-spontaneous process are all are opposite, right? Say if you want to what to say, okay, see, you can ask me, sir, if melting of ice, right, melting of ice is basically, like ice cubes get converted to water, right, liquid water, that is spontaneous, right? But what about freezing of water? Do you think it's a spontaneous process? When I have water and if I convert back into ice, what do you think? Is it a spontaneous or a non-spontaneous process?
It's non-spontaneous.
Okay, that's what we think, right? It's a non-spontaneous process. But please understand, for spontaneous or non-spontaneous, at what temperature that particular thing is happening is very, very important. Okay, see, the first question you should ask me, if I tell you, is freezing spontaneous process, the first question you must ask me is, sir, at what temperature, right? So if it happens at 0 degrees Celsius, right, if obviously the freezing point of water is 0 degrees Celsius, you are not doing anything, right? You're just like, the temperature is there, 0 degrees Celsius, and the water converts itself into ice, right? But if you want to do the same process at say room temperature, right, for that definitely you have to do something, maybe increase your pressure or do something, because we know naturally it happens at 0 degrees Celsius, water actually freezes. You're not doing anything, you're just making sure the temperature is there, right? But the same thing if you want to do at 25 degrees Celsius, yes, that's a problem. That is going to be a non-spontaneous process, because you really have to do something for it to happen, because it's not natural, right? So hope you understand the difference between a spontaneous and a non-spontaneous process. Okay, right, fine. So what the second was telling, right, for a spontaneous process, right, or a spontaneous chemical reaction, since you're talking about chemistry, right, for a spontaneous chemical reaction, right, so what it says is that the universe's entropy, right, should increase. That's what they tell, right? So for a spontaneous process or a spontaneous reaction, if I say universe's entropy is increasing, or in other words, I can tell that delta S universe is greater than 0. Is it not? Obviously, if the entropy is increasing, means obviously, sorry guys, right? So when I say entropy of the universe is increasing, that means the change in entropy of the universe should be greater than 0. That's what you understand. right? See, this is a very powerful statement if you understand, right? uh, or there is, okay, there is one more way also I can put the law, right? Where there is one more way also I'll be able to talk about second law, and that says the entropy of the universe is always increasing. Okay, the entropy of the universe is always increasing. That's what the law says, and it makes sense, right? See, there are going to be so many spontaneous processes happening, right? So all these processes, like sun rising in the east, all these, like anything, any natural processes you have, anything you see in nature is spontaneous. You are not doing anything there. Nature does it by itself, right? So there are so many spontaneous processes happening day by day, right? So obviously the entropy of the universe is always increasing, right? And whenever you see the entropy of the universe is decreasing, and that's the point where the destruction of the world starts, right? The world is no more, right? Now why did I say this statement now, right? So it's because now we know that okay, have you ever heard this? The people say that the galaxy or the universe is always expanding. Do you know
Yes,
this
sir.
theory?
Heard.
Right. Everybody, all big scientists say this. The universe is always like increasing. Though it is always becoming more and more and more and bigger and bigger and bigger. Right. So that's what they say. Right. So obviously, when it grows bigger and bigger and bigger, obviously the chaos increases. And I mean, the sense that I'm telling, the delta S universe is always going to be greater than zero. Right. So like, let me put it like why do I say that if that doesn't happen, that is the end of the world? Now, as simple as that, if say for example delta is universe, or like we'll talk about our Milky Way galaxy, if it is going to become zero, right? So that means there is no change in entropy. Everything is going as such. Nothing is happening, right? Or say if it is negative, whatever it is, right? So what I can interpret from this statement is that the Earth will stop revolving around the sun. See, obviously, right? When something is moving, only I can talk about the increase in entropy or something. When it is something is going to be stationary, right? Obviously, there is not going to be any change in entropy, or even say if it is going to even reduce its speed by a little. Again, under that sense, I will say that the delta S universe is going to be less than zero, negative value, right? So obviously, you know how much complications we will have if the Earth starts revolving or rotating. There is no years, there are no days, there are no nights. It's total chaos, right? It is, I mean, yeah, chaos here in the sense I'm telling problems, right? We will not be able to survive those kind of things, right? So hope you understand, hope you're able to appreciate this statement, right? The second law of thermodynamics, right? So delta S universe is always increasing. The entropy of the universe is always increasing, or the better form is that for a spontaneous process, right, the direction of the process should be in such a way that the entropy of the universe is increasing. Is that cool? Now we will prove this to you. We will prove this mathematically also. Like I take a spontaneous process, any spontaneous process for that matter, right? And I will prove it to you that yes, the entropy of the universe is going to be greater than zero for that particular process. Okay. Now let me take an example. Right? Fine. Any
Sir,
questions till now? Yes.
so if we have to say anything is spontaneous, that means the del S value should be greater than zero.
You
Always.
have to be very, very careful in this. It's not about the system alone. You should take the surroundings value also in this, sum them up. That value you get, that should be greater than zero. It's not like for any spontaneous process, the delta S is zero. No, that's not how you speak about it, right? The entropy of system can be negative or positive. It doesn't matter. But the sum of the entropy of the system and the entropy of the surrounding, the total sum should be greater than zero. That's what I mean by this.
The sum should be greater than zero. If del S individually is less than zero, but that sum is greater than
Yeah,
zero.
no, delta S system being less than zero, delta S system alone, if it is less than zero, no, that is not the thing. It can be less than zero, it can be greater than zero. If it is already greater than zero, well and good. It's a good thing. But when it is less than zero, that doesn't mean that it is going to be a non-spontaneous process. That's what I'm telling you.
Okay, sir.
Is it understood? I think this is a common problem all the students will have, right? So they will say that, say for example, if I have what is it, freezing, right? When I say freezing, what happens there? In freezing, basically a liquid gets converted to a solid, right? And I obviously know liquids have more entropy, solids have less entropy, and people think that sir, that's a non-spontaneous process. Sorry, that's a non-spontaneous process. No, it is not like that. Yes, the entropy of the system is decreasing. Obviously, when a liquid gets converted to a solid, this value is negative, no doubt, right? But if you take the other value also and sum it up, right? For that, definitely this is going to be greater than zero.
Yes,
Okay, I mean,
understood.
yes.
Understood, sir. Thank you.
Okay, right? So don't worry. Now we'll take the same example what I told you. We will take freezing of water at 0 degrees Celsius. Okay, and I'll prove it to you that the delta S universe is going to be greater than zero for that. Is that cool? Right.
Yes,
So
sir.
we'll take an example. Right. Okay. So we're talking about freezing. Right. So you know what happens in freezing? Liquid water gets converted to a solid. Okay. Now please understand. Let me calculate the delta. Okay. Now see, for this, what will be the heat change? Like, what will be the heat change? We're talking about this. So I know basically delta S is equal to Q reversible by T. Yes, right? Okay. Now, okay, forget about reversible. What is this Q value I substitute there? I'm not talking about the value. What is the thing you will substitute here for this? Any idea? Or say if I'm going for any process for that matter, if I have boiling, when I convert a liquid to a gas, at that time, what heat? What is that heat which I'm talking about there?
Like boiling point, sir.
Boiling point is the temperature. Obviously, the T will be, yes, T will be for this, it will be 0 degrees Celsius or 273 Kelvin, no doubt. Yes, that is okay. But what is this heat which I'm talking about? Okay, if you,
Sir,
if you want
like
me,
heat lost or gained, sir.
yes, heat lost or gained is what we are going to speak, obviously, right? So what is that heat called as? There's a specific name for that, for these kind of physical changes, say for vaporization, not mean boiling, fusion, fusion and melt, fusion and
Like
freezing.
latent heat of vaporization, sir.
Yes, absolutely true, right? The only heat which we can speak about is latent heat, right? I don't know how many of you know this. Definitely you should have learned this in your lower classes, right? Whenever you studied about the phase changes, right? So anyone wants to tell me what is this latent heat? Or for this particular process, like when I say latent, this is uh, freezing or fusion, basically freezing or melting, I'm telling, because they are just happening at the same temperature. But anyways, we don't tell latent heat of freezing, we say latent heat of fusion. Anyways, tell me, what do you mean by this latent heat? Or when I say latent heat, or when I say boiling, I say latent heat of vaporization. So what do you mean by this latent heat? Any idea? Okay, so I suppose, like, obviously I don't expect you to know exactly, but still no issues, right? Now let me, like, I'll not take freezing now, I'll take boiling, and I'll explain you latent heat, and then we'll come back to freezing, and we'll continue with all this. Okay, right? So please understand, people. Say I have water at 25 degrees Celsius. Yes. Okay, now I have water at 25 degrees Celsius. Now, if you want to boil it, if you want to convert it into a gas, obviously this temperature has to go to 100 degrees Celsius. Yes, only then the waters will start boiling, right? Okay, now please understand, I assume that I have some 10 ml of water. Okay, I have some 10 ml of water with me, right? Okay, now, okay, the temperature will rise 25, 45, 60, 100, and eventually it will reach 100 degrees Celsius, right? So the 10 ml of water is still there. Yes, right? Now, at this particular moment, when the temperature reaches 100 degrees Celsius, now the boiling starts. Yes, right? The boiling starts in the sense the liquid molecules are going to convert themselves into gaseous molecules at this particular time. The moment the temperature reaches 100 degrees Celsius, the boiling process starts. Till now, it is not boiling. Till now, you are just heating the water. That's what you're doing. Till 25 to 100, you are just heating the water, right? But at 100 degrees Celsius, now what you will understand is, when will you see that the temperature has become 101 degrees Celsius? When will you see that the temperature is rising after this? Any idea?
It starts evaporating, sir.
When it starts evaporating, that means when you're telling that, you're telling that when the boiling is happening, at that time itself, I'll see that the change in temperature. Okay.
Yes, I think so, sir.
Okay, so the answer is, you will see that you will see the temperature will be rising. The temperature will become 101 degrees Celsius only and only after all the 10 ml of water has boiled up. When there is no water left, right? Only then you will see that the temperature will be rising, right? So what I'm trying to tell you is that you 25 to 100, there is a obviously there's a good increase in temperature. 25 to 100, the standard increase in temperature is happening. But once you reach the boiling point, once when the molecules gets converted, the liquid molecules convert to gaseous molecules, till all the liquid molecules have converted, you are not going to see the change in temperature. It is going to stay at 100 degrees Celsius only. The moment all the water has boiled up, there is no more water left. At that time, yes, the temperature will again change. Again, it will start changing. If you keep on heating, then it will eventually start keeping on changing. Right? Now, what do you see? Now, is it like when you reach 100 degrees Celsius, is it like you're going to stop giving heat? Is it like you're stopping the heat supply? You are still heating it, isn't it? Like, obviously you could have seen, you are not if you're going to do it in your kitchen, you are not going to switch off the stuffs, right? The supply of the heat is still moving on, but you don't see that the temperature is rising. The same thing only you are doing here. When I have 25 degrees Celsius, you are not increasing the flame, you are not decreasing the flame, you are still giving that constant supply of heat, right? But here to here, I am seeing that the temperature is changing along with the amount of heat given to you. But when it reaches here, when it reaches 100 degrees Celsius, you are seeing no more. There is no more. Even though you're continuously supplying heat, there is no increase in temperature. That increase in temperature will happen only when all the 10 ml of whatever the amount of water you have has boiled up, right? So now what I'm telling is, you are still supplying heat and you see the temperature is not changing. That means that particular heat is what is called as hidden heat or latent heat. When I say latent means hidden, right? So you are supplying heat, but you are not able to visualize that by the temperature change, right? Whenever you see this, those kind of heats are what are called as latent heats. Okay, hope you understand. Again, I repeat, right? 100 degrees Celsius, you are still supplying heat, but there is no temperature change, right? But that doesn't mean that I have stopped heating, right? So that heat you particularly supply, right, at 100 degrees Celsius, that it is not visualized to you because the temperature is not changing. That heat is what is called as your latent heat. Okay, fine. So how will I put the proper definition for this? Okay, is there any question, people? Everybody understood what do you mean by latent heat?
Yes,
Yes.
sir.
Okay. You want me to repeat again? Anybody? Okay. Let me put it in the. Let me put. Please put it in the chat box if you understood. The heat required to convert a solid to a solid into liquid. Yeah. Like, not completely correct. Yes, you can tell it. Yes, in a nutshell, yes, that's how it is, Vanisha. Right. So, guys, everybody understood what is latent heat. This particular case we spoke about is latent heat of fusion. Mithun Krishna has raised his hand. Is there any problem, Mithun? You have a doubt? Okay, fine. So, hope everybody understood. Shruti, Bavadarani, everybody. Okay, so Mithun doesn't have any doubt. Okay, cool. Right. Fine. So please now take note the definition. Like, there are still more people to what is that? reply me whether they understood or not, right? Because see, I don't want to go through it without you understanding, because that doesn't make any sense at all. Please give me a yes, whomever is okay, cool, cool. Thank you so much. Thank you so much. Right, it's for you only, people. It's because like these kind of things are little important, like not important with respect to marks, like you don't have to give a dash about marks, actually speaking, right? So it's all about you learning it, you enjoying the science, you enjoying whatever you're learning, right? So anyways, right, so hope you understand. At 100 degrees Celsius, right, so you're still supplying heat, but you're not able to visualize that amount of heat between this two stages, between 100 to 101, is what is called as my latent heat of vaporization. In this case, it's called latent heat of vaporization. If I take the same thing here in terms of fusion, it's going to be called as latent heat of fusion. But okay, first we'll take down the definition for latent heat of vaporization. Please take down the definition. Right, fine. It is the amount of heat required. It is the amount of heat required to convert 1 kg of a liquid, to convert 1 kg of a liquid to a gas, at its boiling point, to a gas at its boiling point. Right, I'll repeat the statement. It is the latent heat of vaporization. It is the amount of heat required to convert 1 kg. Actually, people, see, this 1 kg which I wrote can be 1 mole, can be 1 liter, it can be anything, and accordingly, unit will change. Right, so generally in chemistry we speak in terms of moles, because we generally, you know, how do we write your units for energy? We write it as joules per mole, right? So either it can be, you can just write in the brackets, it can be 1 kg or 1 mole, right? Just include that also, right? It can be 1 kg or 1 mole of that liquid to a gas, to its gaseous state at its boiling point. That's the most important point. The most important point in this statement, the most important phrase in this statement is this is happening at the boiling point, not at different temperatures, at the boiling point, at 100 degrees Celsius, whatever the heat you supply, right? That heat is what, not here. This is not the latent heat. From 25 to 100, whatever the heat you supply, that is a heating, some random heating it is, right? But when you reach the boiling point, right, whatever is the heat you supply till you reach 101, till all the water has boiled up, right? So that is what is called as latent heat of vaporization, right? So I can give the same definition for latent heat of fusion also. Now how will I tell it? Now with fusion we talk about melting. So there we convert a liquid, a gas, what do you say, a solid to a liquid, melting, right? Solid ice to water, right? So then there, how will I put it? It is the amount of heat required to convert 1 mole of a solid to a liquid at
its melting point.
yes, at the melting point, right? So if you don't specify this thing, whether it's boiling point or melting point, right, so that's really a problem. That is not how you define it. So this is a small problem, Vinisha, right? And I told you that it is almost correct, but it is not fully correct. Like, this is what I mean by this, right? You have to specify the temperature. It is at the boiling point and the melting point. Okay, fine. Now that we understood latent heat, right, now we have to go back to the proof, that how is it that I'll be able to prove it to you that the delta S universe for a spontaneous process is what is that, greater than 0. Okay, so I think I have to take a page again. Let me do that. Okay, right, cool. So we are taking freezing as we are speaking about, right? So we know enough in freezing, we convert liquid to a solid, as simple as that, right? So for a freezing process, let me calculate what is my delta S system first. Okay, Now delta S system. Now please be very careful. You are talking about heat. It's obviously, I know delta S generally is Q by T or Q reversible by T. Okay, whatever it is, right? So you have to be very careful with this. Okay, in the sense that you have to be very careful with the signs, right? What sign you put. Okay, right? Please understand that when I have freezing, heat is lost or heat is gained by the system.
It is lost, sir, by the system.
Obviously, right? Heat is lost, is it not? Only when heat is lost, they'll be able to go to a more more ordered state, right? So, or in the other sense, when I say melting, obviously you take up heat. Obviously, the opposite process of that is freezing. So definitely in that case, you're going to lose heat. Okay, right? So now delta S is equal to Q by T, right? Now again we know what is the Q you're speaking about. We are talking about latent heat, no doubt, right? But in this case, if it was melting, right? If it was melting, this Q would have been positive value because this heat is absorbed, right? But for this, the Q value, that is the latent heat value which will supply here, you should put a negative value for that because we know the sign conventions, right? Whenever heat is lost, it is negative. Whenever heat is gained, it is positive. So you have to be very careful with all these. Okay, fine. So delta S system will be equal to minus latent heat. Okay, let me write it in short form. Oh, why am I putting a delta? Sorry. Right. So minus latent heat of fusion. Now, this sign is very important, as I told you. If it was fusion, if it was melting, this would have been positive. This particular thing would have been positive. Now, since we're speaking about freezing, where heat is lost, right? So that heat loss is nothing but the latent heat of fusion, and I have to put a negative value. Okay, so I'm just taking out the arrow, right? So latent heat of fusion, right? Okay, now we're talking about water here, right? What is the temperature I have to supply? What is the temperature?
Convert to ice, sir.
You convert to
Ice.
Yeah, so freezing. I'm not talking about freezing of water. So at what temperature this happens?
0 degrees Celsius, sir.
0 degrees
273
Celsius.
Kelvin.
273 Kelvin. So that's the T value you have to supply, right? So the T value which I have to supply is 273 Kelvin. Okay, right? Fine. Now this is my system value. Any questions still here? Any questions? Everybody understood how did I end up with this? Delta S system is equal to, we're talking about freezing process, right? So I'm telling it's minus latent heat of fusion. And I told you why is it negative and why latent heat, why 273? All these questions must be there at your fingertips. Now, do you have it at your fingertips?
Yes, sir.
How about others? Everybody understood why the three questions: why negative, why latent heat, and why 273 Kelvin. Just put it in the chat if it's fine.
Yes, sir.
Okay, cool, fine, cool. So I hope everybody has understood, right? Fine. So this is about my system. Done. Okay. Now when I go to my surroundings, delta S surroundings. I'll put a S here. Okay. Now delta S surrounding. Now please understand the system. The system is basically the vessel, or say the freezer in which we cannot say freezer, fine, whatever the container in which I have the liquid and the solid particles in equilibrium. Like basically the solid and the liquid together is what is my system, right? Now surroundings, right? Now surroundings, now see, you can see that the heat is lost by the system, right? Now the heat lost, where it will go?
Surroundings, sir.
Exactly, right? So for surroundings, the heat lost by the system is absorbed by the surroundings. Okay, again I repeat. Now we see that the heat is lost by the system, right? So obviously, where is that heat? Where is that heat going? It is going to the surroundings, right? So what is happening to surroundings? Surroundings is actually absorbing the heat. right? And whatever the heat is coming from here. Now, in this case, what will be the Q value? Any guesses? Not value. What is the thing which I have to substitute here?
Will it be latent heat of absorption?
Sorry.
Latent heat of absorption, sir.
No, it is going to be, see, this is the heat lost. This, whatever the value which is here, this is the heat lost. And since we are going to indicate that the heat is lost, we
Latent
have a
heat of
negative sign.
fusion, sir. Positive
It is
latent
going to
heat
be
of
latent heat
fusion.
of fusion only, right? But what about the sign?
Positive, sir.
Exactly, right? Because the heat is absorbed by the surroundings, right? So there is no other source of heat here. You understand that, right? There is no other source of heat. Whatever the heat which has been lost by the system is absorbed by the surroundings. Now we said that the heat lost by the system is basically my latent heat of fusion. And that is the only heat which is available that can be absorbed by the surroundings. Yes? Right? 1 second. Okay, right? Latent heat of fusion being a positive value because it is being absorbed. Okay. Now, what about the temperature? Should I substitute 273 Kelvin again?
No,
What should I supply then? And what should be the value there?
should we supply room temperature, sir?
Absolutely true. Right? So obviously freezing happens at 273 Kelvin. It is inside the system. But what is surrounding temperature? Obviously, you forget that container outside the container, right? What is the temperature? Room temperature, right? Right. So we know, say we keep room temperature as 25 degrees Celsius. Assuming room temperature is 25 degrees Celsius. Now what will be this value? This value is 298 Kelvin. Yes or no?
Yes, sir.
Right? So hope you understood this also, right? So please understand, like here, I put a positive value because the heat is absorbed by the surroundings, the same heat which has been lost by the system, right? Now temperature here is not 273, that is for system. That is when the freezing happens, right? But what is the surround? What is the normal temperature around us? That is my surrounding, right? So that is my room temperature. That is my 25 degrees Celsius or 298 Kelvin. Is that okay? Right? Now, if I sum up both of them, now I am going for delta S universe. Now that will be equal to this plus this, right? So if I take latent heat of fusion common, okay, I think I'll take a new page, right? So delta S universe for this particular process. So if I take latent heat of fusion common, right? So it will be the sum of sum of the entropy of the system and the entropy of the surrounding, right? So what happened to the system? It was latent heat of fusion divided by 273 Kelvin. So a minus is there, obviously, minus 1 by 273 Kelvin plus. When I go about the surrounding, it is plus latent heat of fusion divided by the room temperature. That is my 298 Kelvin. So 1 divided by 298. Yes. Okay. Right. Am I
Yes,
doing
sir.
something wrong? Yeah, correct. Right. Now, if you calculate this value, right, if you calculate this value will definitely be greater than 0. Is it okay? Right. Right. So that is how we prove that this, any process, any spontaneous process for that matter, right, is going to be is going to have a delta S value which is going to be greater than 0.
Sir, doubts. I have a doubt.
Yeah.
So, in latent heat of fusion, can it be negative? Latent heat?
No. See, latent heat of fusion, when I say generally latent heat of fusion, it can be only positive because we're talking about melting there, isn't it? Melting process, what happens there? You are going to supply heat. I mean, now it happens at 0 degrees Celsius, but eventually the heat is getting absorbed by the system from the surroundings, right? So obviously in that case, it is going to be positive. But when I say freezing, right? The value is same. The latent heat value is same, but the same amount of heat is lost, right? So there we put a negative value.
So then if we take LCM, the numerator will be negative, sir. If we take
Oh,
LCM.
you're getting numerator as negative.
Yes, sir. It'll be minus 25 by 273 into 290.
Then what are we doing wrong here?
So I think we took surrounding temperature as 25 degrees Celsius, sir.
Yeah. We took surrounding temperature as 298 Kelvin. Yes, we
So
did
it
that right.
should be less than the system's temperature, no, sir. If it has to be positive.
Less than the system's temperature. Yes, if heat is going to get lost,
Then it has to be less.
actually,
right,
actually, true, very true. Okay, now the small mistake which we did is I like when I talk about surroundings, I was thinking about your melting, right? That's the mistake which we did, right? See, please understand, you are talking about heat getting lost, right? You are saying that the heat is getting lost from the system to the surrounding, is it not? Right? So obviously, if you want, it's like something like osmosis, right? So what we say in osmosis, we say that the solute particles are going to move from higher concentration to the lower concentration, right? Same way, when I say heat is moving, the heat will move from a place where I have higher heat content to a place where I have lesser heat content, right? So obviously the surroundings should be at a temperature which is lesser than 273 Kelvin. So I can put it as 272 maybe, right? Okay. I'm really sorry for this, right? I was thinking about melting. Say I'll put it as 272, for example, right? That is minus 1 degree Celsius. Okay, now hope you understand why am I telling this, right? Now please understand, where the system is losing heat, it is going to the surrounding. That is possible only when I have the surrounding is at a lesser temperature, because you're saying that the heat is moving, right? So how the heat will move, what is the direction of heat flow? It is going to move from a higher temperature to a lower temperature. Now the system is at 273, so definitely the surrounding should be at a temperature lesser than that, right? But if I'm same thing, if I'm speaking about in terms of melting, that time yes, surrounding temperature is 290, because who is supplying heat? The surrounding is supplying heat to the system. In case of melting, I'm telling. Okay, so hope everybody understood why is it that I have a lesser temperature than system, because the heat is moving from a higher temperature to a lower temperature. That's how heat generally moves. Yes, make sense? Yes or no?
Understood, sir.
Yes.
Right? Cool. That's a very small thing which you have to do. Yes, correct. So obviously now if you check, yes, delta S universe will be greater than 0. Okay, right? Now we'll quickly do for melting. We'll see what exactly happens there. I know it's already time. I'll just take 1 minute only. Don't worry. Right? So when we speak about melting, right? So obviously we know what happens in melting. A solid gets converted to a liquid, right? So first directly we'll go for delta S system, right? Now obviously now the heat, the system is absorbing the heat. What is that heat? What is the heat here? I'm talking about water. Yes, latent heat of fusion. That's it. But here, unlike last time, the heat is getting absorbed. Now you know that there is going to be a positive value. It's a positive value. Latent heat of fusion is what is the thing which I'm taking. Fusion or melting, both are same, right? So latent heat of fusion is what I'm taking. Now what is the temperature? At what temperature ice melts?
Ice starts melting at 0 degrees Celsius.
Yes, that's the temperature which you have to keep. So again, it's 273 Kelvin, right? So this is my entropy of the system, right? Now when I go for entropy of the surroundings, right? So again, the whatever the heat which is gained here would have been lost by the surroundings. Where is the heat coming from? Definitely the heat is coming from the surroundings. How much heat? Obviously the heat which you have supplied, right? The same amount of heat would have been lost by the surrounding. So in this case, it is going to be minus latent heat of fusion. Why minus? Because surrounding is losing the heat. And why plus is there? Here the system is absorbing the heat. Okay. Now temperature. What is the temperature now?
be room temperature, sir.
Yes. Now, obviously, right now, again, you're seeing that the heat is flowing. Heat is flowing from surroundings to the system, right? So, obviously, the surroundings should have been at the higher temperature. And obviously, it is going to be at room temperature. Again, I repeat. Now, you're seeing that the heat is flowing from surroundings to system, right? So, definitely, surroundings should be at a higher temperature and system should be at a lower temperature. Yes, right. So definitely here the higher temperature, in the sense I'm going to talk about the room temperature, right? Now, if we sum up both of them for getting your entropy of the universe, again, if you see, you will see that this value is greater than 0. Yes. Okay. Right. So like this, again, I can speak about boiling also. Doesn't matter. Okay. Fine, people. So now that we have understood first one of the forms of the second law of thermodynamics, it says for a spontaneous process, the delta S universe is always 0. Now we took 2 examples and we proved it very, very simply. Okay, fine. Any questions? Any doubts?
No, sir.
Okay, fine, people. Right. So we'll meet on, I think, Monday. Okay. So then until then, thank you. Bye bye. We'll meet again.
Thank you, sir.
Thank you.
Sir,
Yeah.
sir, is Monday classes there, sir?
Monday, I don't know, Kana. They will tell you. Monday, 14th is Diwali. 14th
Diwali
is,
holidays and all.
okay. I don't know, Kana. Ask, you must ask Akila only. But if they tell there is a class, I will take class.
Oh,
Okay.
okay, sir. Yeah, okay.
Right? If you convince them that there is no class, then the advantage is yours. Okay.
Okay, sir. Yeah.
Right. Cool. Thank you.
Thank you, sir. Yeah.